All right, so let's go ahead and begin. Hello, my name is Todd Montgomery. I'm the chief architect for a company called Kaazing. Kaazing's been around for quite some time. I'm actually started about 6 months ago as the chief architect. I've known the founders for quite some time. My background actually is I come from high finance. I co-founded a startup that did low latency, high frequency trading. We provided the messaging system for a lot of different hedge funds, prop shops, foreign exchange, things like that. My background is actually in networking and protocols. So I'll be talking a lot about different protocols today. So I come at this with a little bit different of an angle. I've been in the high-performance computing space for 20-odd years, doing high-performance networking for about 15 of that. So this is a little different take on sort of thinking about things at a higher scale. And sort of the way that I usually break things down myself when I'm thinking coming into a new area or an area is sort of what different things lead to which. So in this case, communication patterns are one thing that I notice that has a lot of impact on things like battery life and actually capacity planning and things like that. To give you an example of this, in the capital markets, market data started out in 2004 at around peaks of around 10,000 messages a second. Today we have regular peaks that on average hit upwards of 30 million messages a second. These are small messages, but they come in what are called microbursts. So that huge amount of ramp has a lot of impact on infrastructure. Okay, it has a lot of impact on what you can process, what you can't, how you have to throw things away, how you have to process it. And that's really a communication pattern. Right? It's a very simple one, but it's one that is pretty predominant within market data, which is a piece of every single set of front office trading software. That leads to protocols, because if protocol doesn't support or makes hard to support certain types of patterns, it's really fairly difficult to get them to be efficient. And then that usually leads to architecture. So if you think of it, sort of as this kind of progression, looking at the patterns and looking at the, sort of the protocols and the standards that are out of that, and also look at what architectures figure out. That's kind of the sort of how I would, break things down, and sort of how this talk's broken down. So let's start out by looking at some communication patterns. And a lot of these are pretty simple. What most of us think happens a lot of times when we are, using our devices, or we're, working on a device, or things like that. We usually think of it as, the device is sending a request, getting a response, and doing something. And that's pretty much what really happens. But there are some cases where this is not actually the pattern, and where things are a lot different than that. And so what really happens a lot of times is we have requests that come out. Or conceptually, we have the idea that the infrastructure needs to call out to something else and then get a response. And okay, you may be thinking, yeah, but really, who does this? Well, actually, this happens all the time. How many of you have like a cable box? Right? Okay, have you ever called up support and they've reset your device right then? Your device isn't constantly polling to see if it needs to be reset. They actually send a signal on DOCSIS, which is the protocol underneath of it, to send out and actually to reboot that device. There's lots of other things they can do. A lot of other protocols have this idea where at the lower level, you want to then query some object and get a response, and instead of it being the opposite way around, where the box is always calling back in the infrastructure. And these are just some of the examples of what that simple pattern is. That pattern flips REST on its head, because a lot of times when we think of REST, we think of the device or the browser calling in with a request and getting a response, right? So that's a little bit different. But by no means is that really the only one that we have. We actually have a couple others. This is streaming. We're pretty much all familiar with this, because this is news, stocks, texts, everything else that we see. It's really just a stream of data that's coming from infrastructure down to a device. But we also have the opposite problem, too, which is ingest. And this is actually the one that's more interesting from the infrastructure side as well as the device side. And there's a lot of different examples of this in the IoT space. Temperature, heart rate, web logs, everything you can imagine. Even in healthcare, EEGs and EKGs, all kinds of different pieces of data. Image. Ingest is actually a very difficult problem, because it's really usually a many-to-one problem, or a many to a very small number to make it scale. So it's, it doesn't really, it's not just that, though. So if we think about actually what things mostly look like, they look like this. They look like requests, responses, streaming, ingest, all happening in various ways. And really, if we think about it, we also have to do it at scale, right? So we need a whole lot of different connections and infrastructures that support it, as well as devices that can support it. But if we're engineers and we kind of break things down, what we actually have is something that's really, really simple. Messages go in either direction. They may or may not respond to other responses. They may respond to other work. And the types of messages, they're just types. They're really just, but if you optimize an infrastructure for message, for message passing like this, it actually comes out to be something that's message driven on both sides. So the devices and the infrastructure are both message driven. And this is not new. It's been around for quite some time. It's actually been codified. Their active manifesto, I would assume, sort of ask you to take a look at that if you can. It actually talks about message-driven infrastructure as well as devices that are to build responsive, scalable, resilient, elastic infrastructure, as well as devices and applications. So we'll take a look at this again. The idea that applications can be reactive and can react to events that happen and do just the work that they need to do is kind of central to a lot of the different aspects of what we'll be talking about. So that's kind of the basics of the communication patterns, thinking about them in a little bit different way and sort of breaking them down into very simple chunks. But IoT is actually a pretty broad topic. So let's start out by just sort of narrowing things down a little bit to what we're interested in with connectivity and standards and protocols. These are standards organizations that have different pieces of them looking at IoT. So we have AllJoin, we have the IETF, has multiple different protocols that are in use in different places. Oasis with MQTT, IEEE with IEEE SA work, as well as OMG with DDS. And this is by no means an exhaustive list. This is just showing that there's many different standards organizations. And some of these have actually been doing IoT protocols for quite some time. For example, the IETF actually has RFC 2324, which is actually the Hypertext Coffee Pot Control Protocol. And this is a protocol that started out in 1998, April 1st of 1998. And there are a couple really interesting things about this protocol. First, it is built on HTTP. It actually does its own version of HTTP. It actually has been updated by 7168, which actually adds tea brewing to the support. And actually, it has errata that exists. That's fantastic. There have been implementations of this protocol. It's been around for quite some time. As you can tell, it does some things which, in the REST community, you would think as things that are sort of anti-patterns. It has its own methods, like brew and win. It also has custom status codes like 418, I'm a teapot, if you try to ask it to brew coffee. And that's a quote by the author, really, that it has actually somewhat of a serious purpose. It's trying to identify sort of things you shouldn't be doing with protocols like HTTP. So, it has, but it's been around for a while. So the idea of having things which are, protocols that are specific, to things like coffee pots have been around for a while. But if we look, just beyond the protocols, there's also a lot of additional interest from different companies. We heard from GE, but there's also others, Apple, Open Interconnect Consortium, All-Seen Alliance, and Google. These are just some. There's others as well. And if we want to sort of look at the landscape a little bit, this is sort of what it more or less looks like. This is courtesy vivo things. You have Apple versus Google versus Open Interconnect versus AllJoin or All-Seen. And that's a lot of interest, right? There's a lot of interest. And these are just mostly around interconnectivity, standards, protocols, things like that. So it's fairly crowded. And that means that you're actually going to have instances where people want to reinvent the wheel, right? They don't control the wheel. They don't have any input into the wheel. They don't like the wheel because the wheel's round when the real wheel should be more of an octagon, things like that. Actually, reinventing the wheel can be a great thing, right? This is actually an example of a reinvented wheel. This is a British company that has put together a wheel that has built-in suspension. It's actually a really cool design, right? Kind of a different way of thinking about things. So reinventing the wheel can be a good thing. But it also does cloud the landscape. And history has taught us a couple things about this. The, excuse me, the IoT language, that's probably not going to exist. You know, the IoT protocol, that's probably not going to exist. The IoT runtime, that's probably not going to exist. In fact, anything with the and IoT in it is probably not going to exist, right? It's going to be a fragmented space for quite some time. Now, that doesn't mean that people shouldn't have their own interest and try to go in different directions. Of course they should, especially if what they need is not there. So reinventing the wheel, again, can be a great thing. But we have to make sure that there's not going to be the IoT anything. It's going to be fragmented. So what the Internet of Things already is you know, an environment where it's not one language, it's multilingual. In fact, it's probably going to look like a polyglot, right? Where there's going to be server-side components and device components and front ends, and these are all going to speak in whatever language is the most applicable to that piece. It's going to be multi-protocol and multi-standard. We already see that. It's probably only going to get worse before it gets better. It's also going to be multi-platform. So when we think about it, this is going to be, you know, something which has to support many different types of runtimes, many different types of environments. And it's got to be handled very large scale and be highly integrated if it's to be useful. So this is just breaking things down in a normal way that, you know, should be pretty obvious, or at least hopefully it is. So it means that it's going to be connected, it's going to be integrated. In other words, it's really a great time to be a protocol geek. If you actually like protocols, there's a lot of good stuff that's being done now in all those different standards organizations and looking at different protocols. I happen to be a protocol geek, so it's actually a pretty good time. I'm actually enjoying this quite a lot. If you look at what the definition of a protocol is, it has two very interesting definitions that actually apply to us. The first is, you know, what we would normally think, you know, the treatment and the formatting of data. But the second one there is the describing adherence to correct etiquette and precedence. Actually, that has a lot of applicability to what we as developers do. And I've built and designed several different protocols and implemented them. When you look at how a protocol works, it's not simply just how it looks on the wire and how you specify message exchange. It also is what the correct etiquette around what it's to do and what it's not to do. In fact, John Postal's quote of, "You should be very generous in what you accept and very strict in what you give out," that actually is, you know, central to the actual TCP/IP stack. It's actually built into the protocols themselves. So having that correct etiquette, it's actually very, very important. So we also see this in another way. If you think about REST, REST itself is more than just the protocol, HTTP 1.1. It actually is a little bit more about how you would correctly use it and the correct etiquette. And we've gotten very good about how, you know, to use REST in the right ways and to avoid the bad ways. I'll take a statement here. Protocols are key to integration, and we can actually look at REST as a great example of this. REST is a very good way of integrating things. It's very well understood. People know how to use it. They know what to avoid in lots of cases, and they know how to make things talk to one another pretty well in general. So this is a really good way to show that protocols really can be used for integration. So if we think about, you know, the communication patterns, and now we think about, okay, it's got a lot of different communication patterns, and it's got a lot of different places, and there's going to be a lot of different protocols involved. What kind of protocols do we have at our disposal? And so one of the things you should think about is, well, okay, why should we care about protocols? Well, battery life would be one. So the wrong protocols can hurt a lot. So staying out of a high energy state is really what battery life extension is really about, right? And that is display, radio, and CPU. So we'll ignore display for a moment, okay? If you have apps that are still running in the background on your phone, they're still sending radio signals, they're still using some amount of CPU. Protocols have a lot to do with this. First is, there's lots of different things that we know happens. Many simultaneous TCP connections, for example, they hurt. They actually burn battery life. ASCII encoding hurts CPU and bandwidth. This is just, you know, simple fact. It's a lot less than many simultaneous connections, but it does actually burn bandwidth and it burns CPU. Using the wrong protocol with the wrong patterns hurts a lot. For example, polling. Okay, if you're sitting there and you're constantly polling just to see if something's been updated in the infrastructure, you're not only burning the infrastructure, you're also burning the battery life. Some things that we know do really well. Persistent connections help a lot, and that's because there's fewer frames that are sent on the radio. It keeps the radio into a state where it doesn't have to actually bump up into a high energy state and burn a lot of battery. Well-designed protocols, they actually help a lot more. How much? Well, just as a couple things, MQTT, WebSocket, and a few others, they actually can extend battery life by 2 times to 10 times. They can actually extend it that far just by having a lot fewer things to do and keeping the device out of a high energy state. It's just an anecdotal evidence, but there are lots of different protocols that do that very well. And also binary coding helps save CPU and bandwidth. So this is some of the reasons why we would care. We would care because it actually does something to the infrastructure, or does something to the device, or it does something with the bandwidth or the usage pattern. We have HTTP. It's been around a long, long time. In fact, RFC 2068 and 2016 have actually been replaced with 7230 and 7040. Excuse me. That was in June. We actually have gone through and actually got rid of a lot of the language that was kind of bad in those early RFCs for HTTP, and it clarifies a lot of things that were being done. This is really good. At its heart, what HTTP has is a synchronous request response. So it's kind of bidirectional, but you can't send in each direction at the same time. You can only send in one direction at a time. And you can actually build quite a lot of stuff on top of that. But there is also a need to basically break that synchronous nature of it. And thankfully, we have web services. Web services have also been around for a very long time. And there's seriously a lot of different web services protocols you can take a look at. But inherently, what it tries to do is break the dependency on a synchronous request response, and so that you have maybe a synchronous request and a synchronous response that together can be thought of as asynchronous. Okay, asynchronous request response, kind of. It is small steps. But if you start looking now at protocols which totally break and provide asynchronous nature, WebSocket is the first example here. It's been around since since about 2011, the end of 2011. How it works is it starts as a normal HTTP connect. It does an upgrade, and then it switches protocols, and after that, it's a simple framing protocol that can be sent in each direction. So it allows you to do streaming. It allows you to do ingest. You can also do asynchronous request response on top of it. It really is, TCP over the web. It's full duplex, asynchronous, and it really is a transport protocol. You can run anything that runs over TCP. You could run it over top of WebSocket. That's kind of cool. I mean, you get a lot of different things you can do with it, and that does satisfy some of the things for different communication patterns. It makes it more efficient. Like the anecdote that I said, just changing, from using a REST-based system to using one that has WebSocket has seen, battery life extended, 2 times to 10 times. MQTT has shown the same advantage. But by no means is this done. A lot of the work that was done with WebSocket and the Hi-Bye working group within the IETF has made its way into the next version of HTTP. How many of you are familiar with SPDY, S-P-D-Y? Okay. How many of you know that HTTP 2 is built on SPDY? Okay. HTTP 2, HTTP BIS, is actually the second version of HTTP, and it is asynchronous request and response all the way through. But that's not all it has. It also has multiple streams so that you can use one persistent connection throughout. It has efficient headers. That's called HPAC. And it also has a binary encoding. Now, you've got HTTP 1.1. This works fine. Why would you actually want to move to using something like HTTP 2? It's all in charter. So that when the IETF chartered the HTTP BIS working group to come up with HTTP 2, they gave it certain things that they should do and certain things they had to do or had to produce. But at the core of it was, from experience, an interest in a protocol that retains the semantics of HTTP without the legacy of the message framing and syntax, which has been identified as hampering performance and encouraging misuse. That's why the protocol HTTP2 exists. And it's why it's in right now in last call. Probably by the end of the year, will probably be out as an RFC. So it's not that HTTP 1.1's bad. It's that from a performance standpoint and from being able to build these systems and make them scale, it's kind of an anchor. So you have to look at a different protocol to be able to get that. That's why Speedy came out, and that's why HTTP2 built on Speedy. So the entities behind this, Google, Facebook, Twitter, lots of others that are in the area of trying to do HTTP2. And oh, by the way, you can do WebSocket over HTTP2 as well. There's a draft for that. So asynchronous request, response, streaming, ingest, all in a nice little package, and you can do that over multiple channels or streams. So just thinking about that, you have lots of different ideas of protocols that could be used, but we're by no means done. Oh, no. So we have also MQTT. MQ telemetry transport is an OASIS standard that actually is a broker-based, pub/sub, lightweight messaging transport that runs over top of TCP or WebSocket, and WebSocket is a version 3.1.1 version. And there's also a non-TCP IP version called MQTT SN for sensor networks. So this is another type of connectivity protocol at fairly low level that runs over top of TCP or WebSocket that allows basically pub/sub semantics. So before, when we were talking about WebSocket and HTTP2 and those, we were really looking at things that were just pretty much TCP. In other words, a stream abstraction, a binary stream abstraction. MQTT takes that up a little bit and provides basically a pub/sub interface, so publish-subscribe semantics. That's a little different, but we'll see if actually pub/sub is something that is necessary for IoT. But it does provide a much higher level of an interface for users to use and to build upon. But the IETF also has come out with something recently called the Constrained Application Protocol, in COPE. And that's part of the core working group, which is the Constrained RESTful Environments working group. And over the summer, RFC 7252 has come out. It's been a very busy half year for protocols. And what COPE provides is a little bit different. You have request response in either direction, and you have publish-subscribe semantics as well. It runs over top of UDP and DTLS, which is the TLS version over top of UDP, or WebSocket. There isn't a described version running over TCP. It's very interesting. It has standardized HTTP mappings. So it looks, because as the name, Constrained RESTful Environments states, it's trying to provide a much more interesting HTTP RESTful kind of environment on top. And it has resource discovery, linking, everything else. So it has a lot of the RESTful pieces to it. So it's fairly interesting. There's active work that's being done in this, especially after the RFC has come out, to take this with group communication and lots of other work that's being done around COPE. There's some interesting stuff. We have one more to cover here, and that's XMPP, Extensible Messaging and Presence Protocol. If you use Jabber or you use some sort of other IM agent, you're probably using XMPP or some derivation of it. It has RFC 6120, which obsoletes an earlier RFC. And it's really a presence and persistent streams protocol. It's usually brokered. That's how it's kind of described as well. With TCP, with TLS, with optional TLS, and SASL for authentication. There is actually a standards foundation around XMPP that does a lot of work as well. And then the data payload is basically semi-structured XML, which is fine for these types of protocols if a human's involved. It may not be the best thing for when it's machine to machine, but it's a very good protocol. There's lots of acceptance, there's lots of understanding, and a lot of times that has a better a chance of being something which is used very heavily than something which is less known, but perhaps a better fit. So when we think about protocols, and we just ran through these, fairly quickly. They're protocols like, the normal ones that we think about. But some, if we think about it from a more abstract sense, they're not just traditional protocols. I'll give you first example. Shared memory. Shared memory is a binary boundary. It can be asynchronous. So communicating via shared memory can be a protocol, right? You can run other protocols on top of it if you need to, right? So that can be a protocol. JMS, Java Messaging Service. That's not typically, we don't think of it as a protocol. It is a standard, though. It's an API standard. But you can sort of use it in a way that is, sort of more of a protocol and run protocols on top of it. And people do all the time. WebRTC, it's a protocol. It has a very well defined, but it's a little bit different than some of the things we talked about. AMQP, which is the Advanced Message Queuing Protocol, which is a sort of another messaging type of protocol, but more standardized through Oasis. DDS, which is another protocol I did not talk about, but more of a real-time based protocol. XMPP, which we talked about. ZeroMQ, messaging system, not really a protocol, but sort of falls in the same bucket as JMS. And another protocol that I'm actually working on, which is called AARON. I'm working with some other low latency experts on, should come out fairly soon, that is a reliable multicast, reliable unicast, very efficient protocol for the capital markets. So, their protocols may be a little bit broader than we thought, right? We just think of, when we think of protocols, we think about maybe the IETF, or we think about W3C, and we think about very specific ones. But if we think about it and broaden it a little bit, we have messaging transports that are can cover quite a bit in quite a big area. So that's kind of a lot, right? I just sort of wanted to go through that. These are different things. You may want to be aware of it if you're interested in connectivity. And as we saw, communication patterns, think about those, the protocols that enable them. Last thing here would be architectures. So architectures, if we think about what is being done by a lot of the companies that are doing things at very high scale, or very, not maybe high scale, but high throughput in processing. If I built on my experience in the capital markets, I think of actually microservices architectures. I think of, and here's a pretty good description from Martin Fowler about, what constitutes most microservices architectures and sort of some of the key components of it. It's a little bit out of date, and that's pretty impressive when you think about it. It was only written in March. But microservices is a way of decomposing things down into very small chunks and then having those services that can fail fast. We have a lot of different languages and frameworks that support these concepts. The most well-known is Erlang and Elixir, specifically Erlang. Elixir is a dialect on top of Erlang by Jose Valem. Very good stuff. Communicating sequential processes, a lot of the work that has been around for a number of years, 30 years or more, has influenced the work in Erlang. Another one would be Go as the language. Built in is the idea of microservices. Rust is another example. We also have frameworks that actually support this as well. Akka, which is a Java and Scala framework. Akka Streams as well, which is more of a stream processing. RxJS, Rx, and RxJava are reactive extensions, which are a way of doing sort of more set theory on top of processing. It's very, very useful for these types of problems. So, and the reason why we put them there. So, microservices, we have lots of different support within different runtimes and frameworks and things like that for doing, this same type of architecture. What this architecture looks like is, instead of having something which is more layered and very strict, we look at it in a different way. We still may have layers, we still may have some of those things, but we look at it as more processes that communicate with one another in a little bit more of an ad hoc fashion normally. This is one way of representing it. The idea of a client and a device in a browser starts to break down. So instead of having it as one big monolithic process, we start looking at it as smaller components. And we've been doing this a lot anyway. We usually broke them down in threads as well anyway, but now have them communicate. But now if we move them around so that they can communicate in various ways, and our DMZs and backends and all different components, they start to blur the lines a little bit because now the interaction between these looks a lot more like this as opposed to something which is much more structured and actually wasn't representing what was going on, the communication was going on anyway. And so a lot of the times what we actually have then is a lot of these things communicating and connecting to one another, and guess what? They're using protocols, right? So they're using protocols to connect to one another. So the microservices that these are tend to sort of look some look bigger, some look smaller. If you go to and talk to some people, one question is, how big should a microservice be? And the answer should always be as big as it needs to, but no bigger, right? It should be small, if it can be small. If it has to be bigger because it's bringing in context and state and managing that, then it has to be bigger. It should encapsulate a small piece of a system, though, a very defined well piece. So if we look at this and we say, okay, connecting microservices together with protocols, what does that kind of look like? Well, I call this a microarchitecture, right? What is the architecture of one of those little circles, for example? If we build it up, so this would be the thought process if you decided to step back and see, if I wanted to connect these things all with different types of protocols, I've got to have some way of doing that protocol adaptation between those components, right? But it all has to run inside some sort of deployment. It has to run inside of a container of some sort. And I'm not talking about a container in the Java sense, the Java or J2E sense. I'm actually talking about, a runtime, a language, something like that. And it has protocols on the outside. But that piece has to then understand all those different types of protocols. And then on the other side, it has to be presenting to the logic of that service a reactive message stream. I call that piece a nuclei. And that actually is a system that we've been playing with to sort of support this concept, this idea, and starting to get some others interested in looking at it as well. The name really doesn't actually matter. It's the concept that there's multiple different protocols and it's providing that boundary between the message stream and the other pieces. The protocol aspect gives us an asynchronous binary boundary. It's basically only providing loose ordering. There's no, we're not by loose ordering, I mean things that you would normally get from a, sequentially consistent type of ordering framework like you would normally get in a program or whatever. But the idea of client, server, browser, device, all of them look like this, right? They all could look like this. And there's actually lots of work that's being done in here. There's different things on the client side. Seneca, as well as a whole bunch of other different JavaScript frameworks that are looking at things in this way. They're looking at it as a set of microservices and using things like workers and everything else in browsers. Also, there's on the Node side, or lots of other places where these are starting to filter in. So it's really kind of interesting to do this. And what I think actually is the best part about this is you draw a line here, and that line is an asynchronous binary boundary. By putting a boundary in place, it's actually a good thing. It causes the developer or any designer to think about things in a very different way than they normally would. Just like functional programming, when you say something like, you can't, mutate state. Well, what happens? Well, you have certain restraints on the design that then lead to good things in many cases. So what you do in this case is having a consistent ABI on the other side, application binary interface, and having pretty much the ability to swap things in and out on the other side. It gives you tremendous flexibility so that you can actually do deployment differently. You can actually take a protocol and make it a deployment concern, as opposed to something which is snuck in all the way up into the architecture. This is something that you see a lot of times in certain networking things at a very low level. IP, Internet Protocol, is a great protocol. It runs over about everything. And one of the reasons why is because it's been designed to do that, right? It's been designed to be very simple and to assume a base common denominator, and you can run it over top of anything. It's kind of the same thing. Just move that boundary up, and now you've actually got the ability to change things out underneath of it. Even have things that go from one domain to another. And if you think about having, the situation that we do where it's a very varied environment, this actually can be very, very useful, right? Because now you could have something which traverses from one service to another over top of several different ones by the time it goes through. So kind of interesting. So to sort of sum up, what I would like you to take away is really when we're talking about communicating between the infrastructure components and the different devices, or between the devices or within the infrastructure itself, it looks like simply message passing. And it means that both these sides are really message driven. We should start thinking about them a little bit more like that in those terms. That's it. Questions?
So a lot of the devices currently, I think where you're heading with the container and being able to sort of abstract everything out into this whole thing is a great way to go. But devices have sort of different modes and life cycles in terms of the watch versus Raspberry Pi.
Mm-hmm.
Power profile, usage profile, activity, things like that. How do you think that factor, since you're trying to come up with an abstraction that's still useful for implementation, but not so high up that everything's just been.
Yeah. It's actually pretty difficult when you think about the usage profile of even a phone is so vastly different than a usage profile of like a service in the back end, right? You may, your phone, it may go out of communication randomly. The back end has no idea that you went into a tunnel, right? And then lost connectivity. When you come back, what does it mean that something happened? Like, you ever notice that you turn off your phone, you get on a plane, you turn off your phone, you go halfway around the world, you turn on your phone. It takes a little while for everything to figure it out, but all of a sudden you get a whole bunch of text, right? That kind of thing is also what we're going to see with devices too, right? There's going to be different usage patterns and even power cycles and everything else, which are going to change the way we view. One of the things I've noticed is that a personal pet peeve is applications that don't understand when I close the lid on my laptop that the network is gone, right? So there's applications out there that will totally spin waiting for that connection to come back. And there's other things which are smart enough to understand it went down and they can't really do anything, so they'll wait. So I think it's taken a long time for us to even get suspend mode down on our laptops. It may take even longer to really understand the full impact of that. I think protocols actually do play a very big part of that because there's a lot more usage patterns than with devices, especially wearables and things like that I think are going to be vastly different than what we have seen. So the need for new protocols probably is definitely right on. I don't think we know exactly what they are yet. So yeah, I don't know. But the best current practices around things like dealing with disconnects and reconnect and then TCP state, in other words, keeping a connection state across different connections, things like that. It's actually not that easy, but there are some pretty decent best practices around it. It just takes time. It's much more of the application than it is the protocol, though.
Well, also, a lot of people are talking about TCP and IPv6 all the way down to the end node and things like that. But I think of Apple Watch.
Yeah.
Very, very restrictive, and it's even more restrictive than some of the embedded devices that we've that actually have some service capability.
Yeah.
Before, that these don't necessarily even have that. The user can dismiss something and it's gone.
Yeah.
How do you code to that? So that's what I'm saying. Is it seems like when people are talking about IPv6 all the way to the end, and the end may well be something on the user control that is.
Yeah. The constrained environments are really interesting. If you talk to printer driver developers, they'll talk about the fact that the memory they have is very, very small. So something like, in fact, one of the great discussions, if you're really interested in that, is actually on the HTTP2 mailing list. the working group mailing list. There was several comments that were made about the complexity of HTTP2 and how what that actually means to something like embedding like a web server driver within a printer and things like that. So that it's going to be interesting. Protocol stacks can a lot of times be very small if they're done well. The most I've seen is I've seen people put into just a couple 100 bytes a full UDP and IP stack. So you can do an awful lot once you need to.
So is Kaazing doing anything about that slide you have about messaging?
Mm-hmm.
About messaging, what is Kaazing doing?
So what we're doing is we're working on nuclei. We're looking at protocols because what Kaazing has really been founded on is the idea of protocols and how they interact and providing those protocols for users to do things like messaging over top of, and to and even being able to switch and use different protocols. So what we're doing is we're continuing down that. We actually do believe in the idea that there's going to be a lot of different protocols, and so being able to mediate between them as well as to provide a consistent endpoint where many different protocols can be used, and that layer above where everything above is consistent and everything below can vary at runtime. That's actually what we're looking at, as things around that.
So, for example, are you doing an AMQP buffer thing on your framework on the device?
Oh well, we've had for a long time an AMQP edition of our gateway. So we've already had customers use things like AMQP under JavaScript, on browsers and actually in mobile devices, and being able to use that and then ship it out to an AMQP broker in the back end. So some of that we've already been doing. What this is we're just looking at it as, this is when we look at it, this is what we see. And maybe it's colored by sort of the way that we view it, but yeah, we see that there's not going to be one protocol, it's going to be many, and that we have a good bit of experience in how to do that.
So the question I have, and one of the things you said with XMPP is the fact of if there's human involvement, right?
Mm-hmm.
What was that statement?
Oh, it's just because the payload in XMPP is using XML, semi-structured XML. That was mostly for that.
Okay, and I'm with the XSF. So
yeah.
The question is a lot of work right now on IoT.
Okay.
We have a lot of apps that came out for sensors, actuators, controllers, using EXI, which turns it into binary.
Oh, that's
XML.
awesome. That's great.
And a lot of examples where I actually sit also on working groups with IEEE, ISO, and IEC, where we're now standardizing XMPP for the IoT protocol for sensors, actuators, controllers.
Cool.
As well as we just did it with UPnP. UPnP is now the cloud protocol or XMPP is now the cloud protocol for all UPnP devices, and all join or all scene that you have there is XMPP for the cloud.
Okay.
Everything. So I want to make sure that that's one of the things.
No, I had no idea about the
And a lot of people don't, right?
Yeah.
And I can get, as far as a constrained device, I can get down to, with a full TLS stack, about 80K in flash and 40K in RAM.
That's pretty good, yeah.
XMPP client.
Yeah.
So I'd love to have a discussion with Kaazing or anybody else that's interested in.
Yeah.
Because you got the security put in, you're actually, as a publisher, allowed to authenticate who can get your data from what device, as opposed to you're on the roster, you get whatever you want.
One of the first protocols that after Kaazing was founded that they supported over top of WebSocket was actually XMPP for tunneling XMPP through to browsers at the time.
Yeah.
Mm-hmm.
In fact, that's one of those apps that we just are going to vote now that an application can actually use both protocols, XMPP and WebSocket, in the same session, depending on what that endpoint is and the security needs that endpoint.
Good. Yeah, I didn't know about the binary encoding, which I'm glad to see because, coming from more of a background that's, very heavily on the low latency side, the cost of parsing in some systems will be like 70%, 80% of the time of a latency profile, which is tremendous. And when you can get rid of some of that, it really shows. Yeah. That's great to hear, yeah. That's good. Thanks. So, any questions? Any more questions? Yeah. So protocols and security go hand in hand. A lot of different protocols have really bad security models or none at all. Yeah. Well, WebSocket subsumes, sort of either the HTTP, authentication and everything that's already in place, but then you have things like re-authentication and everything else that come up. Yeah. 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 Yeah, and you don't want to do something like since it's a long-lived connection, whereas HTTP assumes a short-lived connection, you don't want to actually have the cost of tearing the whole session down, reestablishing it just to do re-authentication. You'd like to have some sort of challenge response that's done inside the protocol. Luckily, WebSocket has extensions that can be used for exactly that, and that's really what we do. We actually have done that and used WebSocket extensions to provide those types of different aspects of that. But yeah, other protocols, it's very interesting when you read like an IETF doc has to have a security implications section. It has to have, here's what the security implications are, which is much more than just authentication, right? It's a whole bunch of other things as well. But some other standards groups don't have that, right? Some do. I'm sure XFS does because they have to. Yeah, but others don't. I mean, Oasis doesn't really have a, you have to fill this section out kind of thing. So yeah, protocols and security are one of the things that you can't really be around protocols without looking at some security aspects. It depends on the protocol. In for the Kaazing gateway, what we've done is WebSocket extensions and going with whatever the protocol is and looking at the security of that protocol and then extending it with extensions if possible. AMQP also itself has, for example, annotations that can be done on top, or like AMQP 1.0. So those annotations can be used to carry security information for like on a per topic basis, things like that. So it depends on the protocol. You can't really take an elephant and squeeze it into a box, right? You kind of have to figure out how it's going to fit. And yeah. Anything else? All right, thanks.